Hi.
How you doing?
Good. How are you doing?
I'm doing alright.
Do you need a review sheet?
No, I got
You got Matthew over there. So we have two night class students. So
it.
it's all good. So these will be posted because they might be kind of hard to all write down. But usually this will probably take about 35 minutes or so, I think. So the first thing about those energies, I kept calling them cousins. You probably need to know kind of from shortest wavelength to longest wavelength. Know them in order. And then the next term actually goes along with that too. With regard to frequency and wavelength, they go together. Let me see if I can do this right. Good. Okay, so green there says frequency. The gamma rays, remember, basically, a lot of them pass a point in 1 second. That's called hertz, number per second. And for microwaves, they're so big that actually not very many of them pass a given point in 1 second. So they have a low frequency. And then with regard to wavelength, kind of up there in purple, the gamma rays, the most energetic, have the shortest wavelength, and the radio waves have the longest wavelength. And then I finally decided to kind of tie it up together in blue, kind of ignore that up in the corner. In blue, underneath the whole cousins thing, I said for any given energy, if you take its frequency times its wavelength, you get, what's C? Speed of light. Is that not cool or what? They're all traveling at the speed of light if they're traveling in a vacuum. And for any given energy, you take, again, its frequency times its wavelength, and that'll be equal to the speed of light. So structure of an atom, I kind of drew up there, squeezed it up in the upper right-hand corner. Structure of an atom, we only talk about 3 particles. So atoms have what we call a nucleus, and inside the nucleus are the protons and the neutrons, and outside the nucleus are the electrons. So then a couple of terms related to that, atomic number and atomic mass number. Now, they're both whole numbers, they're both integers. Atomic number is you're counting the number of protons in the center or in the nucleus of a given atom. And once you count the number of protons, you know what element that atom is. I just think that is so cool. Okay, so that's atomic number. And then mass number, you're looking just to the nucleus, and I kind of see where it says atomic mass number up there in blue. Basically, you're honing in on the nucleus, and you're literally counting protons, and then you're also counting neutrons. Okay, so that's the atomic mass number. The next term up there, light interacting with matter. And again, when we say light, actually, we're saying all of those different types of energies. So light could be gamma rays, or light could be radio waves. But how that energy is going to interact with the matter depends upon what the energy is and what the matter is. But they're listed 3 possibilities in blue there. That matter can either just let that energy go on, which we call transmission. That matter can absorb the energy, or that matter can just kind of interact with that energy and scatter it, redirect it. So scattering and reflection are both just kind of types of redirection. Then the next term, and actually I brought in a figure from the internet. Okay, so it's a busy figure, but I'll kind of talk you through it. Okay, there are 3 different types of spectra. Okay, and there's Kirchhoff's first, second, and third law, which I wouldn't worry about that. But this says continuum spectra. We learned it as continuous, continuum, continuous. Okay, but the thing about those continuous spectra is they don't have any lines. But what they are great at, and you see it there in kind of a maroon color or purple color, what a continuous spectrum does do is it gives us that kind of a signature of what temperature an object is. Okay, I call it a black body radiation curve sometimes. Remember that one figure I got so excited because it showed like kind of the thermal signature of 3 stars, the hot star, which was blue, medium-sized temperature star, which is us, yellow, and then a red star. And then it showed the human, okay? I just think that is so cool. Okay. So that's continuous. And then we have these right here, okay? We have emission line spectra and absorption line spectra, okay? They are both, what they have in common is the electrons are making them happen. Okay, the thing for the emission line spectra is energy is emitted, and you figure, well, how do you get energy to emit? Well, basically it's energy that's falling back down and being chillaxed. Okay, electrons are falling back down to a ground state, and they're emitting that light. So the thing about absorption line is basically electrons are sucking up a particular energy. That's why you kind of see it there, that particular color, because it's a particular energy. Electrons are sucking up that particular energy and being promoted. Okay, so that's the three different types of spectra. And actually, that also covers the electrons transitioning between energy levels. Okay, on to my cheesy diagram, okay, of the two types of telescopes. So you see my two types of telescopes here, okay, and then under here. Of course, you would say kind of the green and the red, the two types of telescopes are the ones that use mirrors are reflecting, and the ones that use lenses are refracting telescopes. That's cool. Okay. And then down here I drew, this is my mirror back here. Okay, basically what reflecting telescopes do is light comes in, hits the mirror, and then it's bounced back to that little green dot is a focal point. Okay, so that's my reflecting telescope, and this is my refracting telescope, where you have a lens and light is brought down the tube to, again, a focal point. Okay, so my refracting and my reflecting telescope. And then so the whole idea of what a focal point is kind of drawn here, because that is a term. What is a focal point? It's basically where a telescope directs the information, bless you, that it's gathering. And then the next term related to telescopes is angular resolution. I have it up here in red. It's just for a given telescope. It's the angular resolution of a telescope is its ability to resolve detail. Then I have this redshift, blue shift. Okay, let's see if I can do this. I think if I do this. Okay, so starting with redshift. Basically, redshift occurs when the thing emitting the sound or when the thing emitting the light is moving away from the observer. Then you get your redshift. Okay, something's moving away from you. It gives you a redshift. Now, if what you're looking at is giving you kind of these spectral lines, that redshift is going to cause those lines to go to longer wavelength. We compare that to blue shift, and blue shift is where the source is moving towards the observer. Source is moving towards you, and those little wavelengths get squished. And so what you're going to see is any spectral lines will be shorter wavelength. And then the last term I put up there in the corner, because it says, why do we put telescopes like Hubble orbiting the Earth instead of ground-based telescopes? And so kind of listed up there have three things. One is Earth's light pollution, getting worse and worse. And the other is the Earth's atmosphere has turbulence. It's just not even. And so that's a hard thing to combat. And then for the third one up there, that circle with a plus in it, that's the sign for Earth. That's Earth's atmosphere absorbs energies that we might want to look at. Okay, because the Earth doesn't let, for instance, gamma rays reach the surface. So if we were going to have a telescope look at gamma rays from the cosmos, it's not happening on an Earth-based telescope. So again, this is available under doc sharing. Did you get it, Callie? Okay. Okay. Chapter 6. First term. Solar nebula. Basically what our solar system came from. Okay, so solar nebula. It's the stuff that formed our sun and the planets and the miscellaneous stuff that actually, in Unit 3, we're going to talk more about comets and asteroids and stuff. So I'm hoping that you have a fix on, in order of their abundance, and I'll kind of pause it with the first two, how abundant was stuff in the solar nebula. Most of the solar nebula was just hydrogen and helium. And it wasn't until just this semester I'm like, wait a minute, that's still the situation. If you take a bird's eye view at our solar system, that's what stuff made our solar system. came from the solar nebula. But I put those in green because they would not condense, or they'd still be a gas if you're close to the sun, this side of the frost line. So the other two things, and they're less abundant or less amounts in the solar nebula, were those rocks and metals, which of course we hold near and dear to our hearts. No pun intended. So with regard to relative amounts, they were kind of down on the list. The next term, collapsing solar nebula. Okay. A couple of things. I'll just put those two things up here. And it's like the skater kind of, where the skater has a footprint like this with her arms out and brings her arms in. She goes faster and faster. Okay. We talked about the conservation of angular momentum. So she goes faster. But the other thing we talked about in the last unit was this idea of gravitational potential. And actually we kind of brought it up in chapter 6 again. As the nebula was collapsing, okay, to ultimately form our sun and the planets, kind of has a smaller footprint, some of that potential gravitational energy was transformed into thermal energy. And so that's actually why it got warmer. Okay. So for the next one, I went ahead and brought in a figure from your textbook. Okay, so what you're looking at is kind of the early on before the sun. I'm going to make it dark in here, I think. Bless you. Bless you. Early on before the sun turned on its solar wind, we kind of had an assortment of kind of dust to go ahead and via accretion make the planets. But actually around the Jovian planets, they got larger, okay, and so actually they had their own kind of mini accretion disk. Okay, so those cool moons we looked at today in lecture, okay, well, some of us looked at today in lecture, that was formed in that little accretion disk around Jupiter. Okay. All right. So anomalies, and I think there's two of them, I think. Anomaly just means like, now, how did that happen? So a couple of them, remember we said that Earth's large moon is weird, okay? Why does it have such a large, beautiful moon? And then we talked about kind of what's called the collision ejection theory, or actually we talked about that before we got to this chapter. The fact that the way we got our moon was basically we were whacked, okay? And the thing about getting whacked to form our moon, there was all sorts of whacking going on early on in our solar system's history. The other thing, and it's the same reason, lots of sort of chaos, I call it chaos, is Uranus got its tilt. Okay, so if you're asked what are the anomalies, those are the two anomalies. Okay, so a bunch of stuff here about the two types of planets. Okay, and actually, I think you guys are kind of probably good with this. Okay, the two types of planets. The inner planets are rocky, we call them collectively the terrestrial planets, and the outer planets are the Jovian planets, and they're primarily made of gas. And I think what I've drawn up there, maybe is there more? Let me see. Would probably get you what you want to do on the test. Okay, so speaking of chaos, with regard to Earth's water, we really think that Earth got its water basically by ices that were deposited by stuff that crossed the frost line, basically. So it's kind of exciting. We got our water from bombardment with icy bodies, as things were just kind of going willy-nilly. The term accretion, I was thinking Grecian formula, but accretion is basically, in general, a gathering of material to create a larger rocky body. Kind of like taking snowflakes and making a snowball sort of thing. Frost line. Frost line basically separates two temperature zones. It separates the warm temperature zone, where only rock and metals could condense, from the colder temperature zone out away from the planet. So in black it says, to kind of summarize, what the frost line does is basically separate our 4 rocky planets from our 4 Jovian planets. Now, since we've kind of talked about our solar system a little bit more in depth, does it make sense then that like Pluto should be, I mean, because you think the terrestrials and then the gaseous and then there's Pluto, which is basically like a comet. So the last term up there, and again we're going to talk more about this for kicking off Unit 3, but there's the Kuiper Belt and the Oort cloud. So this is a figure from your textbook where in the middle is the sun. That blue line is Neptune, the last planet, right? So kind of drawn to scale, we have all of these kind of crumbly things to explain. So the thing, this crumbly right here kind of is called the Kuiper Belt, and it lies in the plane of the ecliptic, basically the same plane that the planets orbit. The thing in orange there is called the Oort cloud. So let me ask you this. This is kind of how the test question goes. Which type of comet? These things hold comets. The Kuiper Belt holds comets. The Oort cloud holds comets. Which one's farther away? If a comet is in the Kuiper Belt or if a comet is in the Oort cloud? Oort, yes. Okay. So it's just kind of a preview of that. Okay. Next chapter. All right. I know, it's a big one. Okay. So with regard to Earth's tectonics, actually I kind of took those first 3 terms and kind of combined them. So Earth's tectonics counts on the slab, which actually is not just the crust, it's also the upper part of the mantle, lithosphere, moving. Okay? And it moves via convection. So kind of those 3 terms all kind of go together. I brought that figure in from the internet because I thought it was pretty good. So to kind of talk about convection, okay, notice that the Earth's core is hot, okay, and then convection is basically warm material rising, okay, and then it cools down and then it sinks and it forms these cells, these convection cells, okay. But was it like 100 million years or something to do one loop for the same material to go up and cool down and come back down? That's craziness. So up there in green, I have lithosphere equal plates moving. Okay. The next one, planetary differentiation. Okay, I brought in the figure from your textbook for planetary differentiation, or actually not quite planetary differentiation. Those blue checks there from the figure from your textbook is to kind of emphasize the gray is the core, and kind of the orange around the gray is the mantle, and then that little bit of kind of tan looking is the crust. All right. Now on to planetary differentiation, kind of in tan there. It says that basically the terrestrial planets used to be molten. They didn't have, and even the little ones, okay? And so just kind of like if you have 2 liquids of different densities, kind of oil and water, the more dense material sank because it could. That's called planetary differentiation. Then the next one, with regard to surface erosion, I think I wrote down 6. Surface is like the thing we're walking on, right? The planet's surface. And the term erosion kind of means like it's I keep using the word resurfaced. So ways that actually the surface of a planet, including the Earth, can get a fresh start. Okay, volcanism, tectonics, wind, water erosion. Remember, for water erosion, I just am amazed at the Colorado River carving out that amazing Grand Canyon. Okay, debris, that was like kind of, if you have flooding, houses kind of move and they make their own paths. And then ice would be our ice ages. The next one, Mercury's cliffs. Okay, kind of in gray here. Mercury has these features called scarps, S-C-A-R-P-S. I can't remember if you necessarily, I don't think you need to know that term, but they're kind of like cliffs, Okay, these are cliffs, scarps are cliffs, and they are a result of Mercury cooling. The next one, quite simply, I want you to recognize that a big boo-boo that has the proper name Caloris Basin, that it is on the planet Mercury. What planet is Valles Marineris on? Take a guess. It's the busy planet. Nope, not on Earth. Would be the busy planet. It's on Mars. Yeah, Valles Marineris. It's on Mars. But the other thing to kind of finish that thought and pick out the right answer on your test is it's that boo-boo near the equator. It's a trench. When I think of Valles Marineris, I kind of think of a supersized Grand Canyon. Mapping the surface of Venus. This is where I'm kind of explaining to people who are in review sessions like this that this will be one of those that'll be extra credit. The way extra credit will work is that you answer it correctly and I won't count it as one that you had to get correct. So in other words, there'll be fewer, I'll divide the number you got correct out of fewer. Does that make sense? Points. Okay. But because I didn't make it into my notes, but I think I mentioned in class that Venus has those thick clouds. So you're like, dude, how are we supposed to have those cool surface pictures of Venus? Radar. Looks like Vadar. That's Radar. Yeah. So the only way we know it's got kind of those quiet volcanoes right now and kind of little bumps and a few craters is by basically sending a satellite in orbit and sending down, kind of looking for echo. Greenhouse gases. Greenhouse gases trap otherwise outgoing heat. Basically, all of the planets are getting shined on by the sun, and some of that sun's energy interacts with the planets and basically turns into thermal energy. And if there are greenhouse gases present, then they can go ahead and act as a blanket and kind of trap that energy, or that thermal energy. No greenhouse gases, that energy goes into outer space. How did Mars lose its atmosphere? So you want to be able to kind of tell this story. I usually break it up into 3 parts. Okay, starting with the fact that it cooled, Mars cooled faster than the Earth because of its size. And then since it cooled, it solidified, and the solid core could no longer create a magnetic field. So the solid core basically couldn't create that magnetosphere. And then the third and final kind of thing that nail on the coffin was that without that protective magnetic field, the sun's solar wind basically blew the Martian atmosphere down the road. Which makes me kind of think of like a buildup of material at the edge of what we call the sun creates what we call a heliosphere, a big bubble that the solar wind kind of identifies, distinguishes the edge of. So there's where Martian atmosphere is. Without a magnetosphere.
Oh, okay. Yeah. I see it now.
Okay, flowing water. Actually, no pun intended, but Earth has current flowing water. Get it. Mars has had flowing water in the past. The next one's also going to be worth extra credit because I couldn't find in my notes, I don't think, where I actually say what Phobos and Deimos are, but they are the Martian moons. And this is a figure from your textbook, and one of these, and these aren't drawn to scale relatively speaking, so one is smaller than the other. Martian moons. The next one is also, I couldn't find where in my notes this semester I explain why Mars is red. But Mars is red because of a process that happens here on Earth called rust. Okay, the element iron and some water needs to be present. Combines with oxygen to form iron oxide. And that's what rust is, and actually that's what is the red material on Mars. So, this was a big chapter. The last one, actually, then, is the magnetosphere, or magnetic field. Those terms are actually synonyms. Okay, so I brought in the figure from your textbook about Earth's magnetic field. Okay, and then right here in purple, this is important. The magnetic field, or the magnetosphere that the Earth has, planets like the Earth can only have it if those two criteria are met. Okay, one criteria is that, remember Mars, it solidified and it no longer had fluid near its core. Okay, so the planet needs to have some sort of fluid near its core. Okay, and then the other criteria is that it needs to be rotating sufficiently fast. Venus, we think, has probably, its core is not solidified, but it's not rotating. The way I've heard it is that it doesn't have a magnetic field, Venus doesn't, because it's not rotating fast enough. So with regard to which planets have this, the Earth has a strong magnetic field, and I went ahead and this must have been something I read or something, but I went ahead and said Mars has a magnetic field, but it's very weak, very wimpy. LOL. All right. See, now the last one. Is that not short or what? So the gaseous planets. And I think we've said this a few times in the notes, that even though we think of moons, the Galilean moons orbit Jupiter, and we think of Saturn's beautiful rings, honestly, all of the gaseous planets have moons and rings. So with regard to Jupiter's the most massive, okay, but with regard to comparing Jupiter to Saturn, actually Jupiter is more dense. And density, we talked in class, is basically it's got more stuff crammed per a given volume. So in order to kind of explain how Jupiter can be more dense than Saturn is kind of this pillow scenario, where basically the pillows are the hydrogen and helium, okay, that kind of congregated to the planets, Jupiter and Saturn. Jupiter has more pillows. So honestly, even though pillows are light and fluffy, by the time, if you keep adding pillows, that bottom pillow is going to be pretty squished. Your material is going to be pretty much, like I said, kind of compacted. Okay. The next one, what drives Io's volcanic activity? In the daytime class, we just talked about this just today. Okay. Tidal heating drives Io's volcanic activity. It's spewing out those sulfur-containing compounds. So on Earth, we talk about tides because of the moon's influence. Okay, gravitational pull of the moon to the Earth's oceans. Well, the tidal influence here is from the planet Jupiter and Io's fellow Galilean moons. So basically, it kind of has this kind of flexing thing going on. Composition of Saturn's rings. They're individual particles, not a solid mass. Okay, and I usually like to say that there are just kind of plain old rocks there. But more importantly, what makes it so reflective is either those rocks are coated with ices, literally, like, or they're just like chunks of ice out there. And like a fresh snowfall, who doesn't love a fresh snowfall? I mean, you know, the snow may drive us nuts, but it is beautiful, I think. And then the next one's quite simply methane, is what gives the blue planets their blue look, Uranus and Neptune. And Triton orbits which planet? It's not Earth.
Saturn.
Almost. That's Titan.
Pluto.
It's not Pluto.
Neptune?
It is Neptune. Very good. And Triton sounds very similar to, and I think I kind of jot it down here in red. Titan is like around Saturn, and this drives me nuts because Titan is more popular than Triton. But I want you to know that Triton orbits Neptune. And the other thing about Triton, and I didn't put it up here, is it's got that kind of cantaloupe look to it. Okay. All right, Galilean moons. There they are. Okay, and the last term's up there too. So Galilean moons, I would have down on your note card the 4 Galilean moons. And then also this last subject here, tectonics of icy moons. In today's class, we kind of touched on this. The fact that, tectonics that we know about is basically slabs of lithosphere going on liquid mantle. Okay? But you compare that to, and if you just want to make one comparison, one noted difference here, is this is kind of the setup for those icy moons where there might be fish down here. No. Well, there's liquid water, basically the slabs are moving on liquid water instead of liquid mantle. Okay? So I just think that is so cool.
What do we write down for the last one?
Let's see. I kind of circled liquid water or warm convecting. It's convecting ice, but I think liquid water for is moving those plates. Any questions? I'm going to show you while I got you here. No, I can't, because I don't have access to the internet. But these 4 screenshots of, chapters 5, 6, 7, and 8, those are available for download under doc sharing. Under doc sharing, there's something that says unit exams, and those are here. Okay? Alrighty. Oh, did everybody sign in? There's a little clipboard there. Sign in, okay.
You have a question.
Yes.
What is due this coming Thursday?